Therese Landry, and she's going to tell us about analysis on fractals. I'll let you read the title yourself. It's long.
Piecewise C1-Fractal curves, Lapidus had spectral triples, and the Gromov house door for. So thank you very much to the organizers of this program for giving me this opportunity to talk about my work with my collaborators. So a key tool in the development of analysis on fractals is a development of a theory of their finite approximation. And that is because there are a lot of instances of natural phenomena that fractal geometers would call fractal, but of course, a theoretical fractal is an infinite object, and any occurrence of fractality in nature will by necessity be finite. And as we all know, there are many natural processes which can be modeled by differential equations, but classically the solutions of such equations are often formulated in terms of operators on smooth manifolds. So another motivation for the development of analysis on fractals is the extension of such methods to fractal spaces. And
sorry, you need the mic. Oh, they can't hear you. I'm sorry.
Okay, sorry. That might have been part of being ready to go anytime.
It's on.
Okay, do I? Okay.
That should be good. I'm sorry.
Okay, so we're going to take it from the top once more, this time with microphone. Maybe you can check if they can hear you.
Can you guys hear me? Or clap your hands if you can.
Yes, we can hear you. Can you hear us?
Yes.
Yeah, we can hear you. Great.
Okay, well, all right. So, why develop? So a key tool in the development of analysis on fractals is development of a theory of their finite approximation. And that is because there are many instances of natural phenomena that fractal geometers all agree are fractal, but a fractal is an infinite object, and by necessity, any occurrence of fractality in nature will be finite. And so also, there are important natural processes which are modeled by differential equations, but classically their solutions are often formulated in terms of operators on smooth manifolds. So extending these methods to fractal spaces would allow us to better be able to understand how fractality arises and evolves in nature. So in service of these goals, my work uses tools from non-commutative geometry, in particular spectral triples, because those can be viewed as a generalization of differentiable structure, and the Gromov-Hausdorff propinquity, which can be viewed as a section of Hausdorff distance to function spaces. And that's because accessing the geometry of a space, like a fractal through its function space, removes any obstructions that might occur from the scarcity or absence of sufficiently well-behaved paths on the space. So here's an important test case for analysis on fractals, and that is the Sierpinski gasket. And that is because there actually does not exist any one definition of fractality that captures all the objects and processes that fractal geometers agree are fractal. So there are many non-equivalent definitions of fractality, and the Sierpinski gasket satisfies several of them. So for instance, it is self-similar. It also has fractional Hausdorff dimension, so there are actually fractals that do not have fractional Hausdorff dimension. And it can also be realized as a unique fixed point of an iterated function system, in particular this one. So what is our framework for studying Sierpinski gasket type fractals? Well, that is the class of piecewise C1-fractal curves. So again, the Sierpinski gasket is the motivating example for this class of fractal curves. It is a compact length space, and it's a compact length space that exhibits the following properties. So first of all, the space can be decomposed into a countable set of parameterized curves, and it can be enumerated with respect to decreasing arc length. And the role of the second axiom is that it allows you to get a handle on the geodesics of the space. So it tells you that an implication of it is that the endpoints of the parameterized curves are dense in the space. And it also allows you to write the minimizing geodesics between 2 points as a concatenation, a countable concatenation of the parameterized curves. So besides the Sierpinski gasket, another very important example of a fractal that falls in this class is the harmonic gasket. And this is fundamentally different from the Sierpinski gasket. First of all, it is self-affine rather than self-similar. But it's also of fundamental importance because this is a fractal on which there exists the most well-developed measurable analog of Riemannian geometry, thanks to Jun Kagami. So thanks to Jun Kagami, for the harmonic gasket, we have measurable analogs of Riemannian gradient, volume, and measure. Okay, so how might one approximate piecewise C1-fractal curves? So this is the usual realization of or approximation of the Sierpinski gasket as an increasing union of finite graphs. And so one of the things that Lapidus and Latrémolière and I did was come up with, we enriched the framework of piecewise C1-fractal curves with the notion of approximation sequence, so that a sequence of finite graphs would support also other structures like compact metric spaces and our quantum analogs of differential structures, i.e. spectral triples, that those would also approximate those on the limiting fractal curve. So even if we have an enumeration of the parameterized curves by decreasing arc length, that doesn't mean that any subsequence of these parameterized curves is going to give us an approximating finite graph. So you have to be careful in in determining up to which parameterized curve in that enumeration to take in order to, even for the Hausdorff distance, come up with a sequence of finite graphs that approximates the fractal curve. And so here is our definition of approximation sequence. So we have a piecewise C1-fractal curve. We have a decomposition of it into parameterized curves. So our notion of approximation sequence is a strictly increasing function. And it is one that tells us up to which parameterized curve to take our union over to define our finite graph, and such that the corresponding sequence of finite graphs, when we equip it with the geodesic distance, exhibits the following properties. So this tells you that the vertices in each finite graph are sufficiently well distributed throughout the finite graph for our approximation purposes. And also that when you lift the vertices of each finite graph up to the level of the limiting fractal curve, that the geodesic distance remains the same. So as we'll see in a later example, it turns out that the inclusion map for each finite graph, that it's actually not embedding. So here's an example of an approximation sequence for the Sierpinski gasket. So, namely, first take as your set of parameterized curves, first edges of length 1, then of length 1/2, then of length 1/4. And so what increasing function describes the sequence of finite graphs? So that's in particular, this one does the job. And so this increasing function is such that we can capture this particular sequence of finite graphs. And it turns out that this particular approximation sequence happens to also work for the harmonic gasket. And it was really in trying to come up with, to generalize what properties were needed to go from even just be able to deal with the case of the harmonic gasket, that we had to come up with this generalized notion of approximation sequence. Because you can see here from the self-affinity that it's not quite as predictable as it is when you have the self-similarity. And that's another reason that the harmonic gasket is important, because in a way it's a relaxation of this strict self-similarity that's normally associated with fractality. So in Riemannian geometry, intrinsic metrics play an important role. And for fractal curves and finite graphs, a natural choice of intrinsic metric is the geodesic distance. So now this is where the conditions on the vertices, why the importance of some of those might become apparent. So for instance, this point and this point, those are not vertices on this finite graph. But when I lift them to the fractal curve, then with respect to the geodesic distance, it gets shorter, right? But if I consider only vertices, like so this one and this one, when I lift it to the fractal curve, the geodesic distance remains the same. So even at the level of Gromov-Hausdorff distance, convergence for these corresponding compact metric spaces, that's still a non-trivial sort of problem. And one which was a motivation for our choice of definition of approximation sequence. And so that said, in order to be able to access these spaces via the perspective or lens of non-commutative geometry, we need to make the appropriate choice of function spaces. And these function spaces in particular, as we'll see, happen to be very important examples of certain function spaces. So many fractals are compact Hausdorff spaces, and the topological properties of such fractals can be recovered. And so their topological properties can be recovered from algebraic properties of their spaces of continuous complex valued functions. And well, see it like such spaces are examples of C-star algebras. So a C-star algebra is a Banach algebra, but it comes equipped with a star operation. And this star operation is conjugate linear, it's involutive, it's anti-multiplicative. And then what really distinguishes a C-star algebra from a Banach algebra is the way it determines the norm on the C-star algebra. So the C-star identity and this intertwining with the norm property is what really distinguishes C-star algebras from Banach algebras. And some examples include, well, the complex numbers and C of x for any compact Hausdorff space x, and by n matrices over C, and the space of bounded operators for any Hilbert space. So in the setting of C of x, the multiplicative linear functionals play an important and characterizing role. And morphisms between unitary C-star algebras, they're given by algebra homomorphisms that preserve both the unit and the star operation. And so therefore the foundation of non-commutative geometry is the Gelfand-Naimark theorem, because this gives you that every unital commutative C-star algebra is star isomorphic to C of x for some compact Hausdorff space x. And so therefore, by analogy, the non-commutative spaces exist in correspondence with the non-commutative C-star algebras. And so one example is that, well, the complex numbers are star isomorphic to the space of continuous complex valued functions for a singleton. But on the other hand, if I just take the vertices in the Sierpinski gasket, well, that is not a compact Hausdorff space. And so therefore, the space of continuous complex valued functions over the vertices is not a unital C-star algebra. Has a unit.
Unital means it includes the identity. What is the unit? What's a unit?
It would be the constant. Okay, so our generalization of differentiable structure from non-commutative geometry is that given by spectral triples, which are due to Kahn. And so a spectral triple, the main ingredients are, first of all, unital C-star algebra, Hilbert space, unital representation of the C-star algebra's bounded operators on the Hilbert space, and a distinguished operator on that Hilbert space with the following properties. So in analogy with the denseness of C1 functions in C of x, the set of elements in the C-star algebra for which the commutator with this operator is densely defined and extends to a bounded operator on the Hilbert space is dense in the C-star algebra. And the operator has compact resolvent. And what this does is that it allows you via the methods from non-commutative geometry to extract information like non-commutative analogs of metric and measure. And so when the representation is also faithful, then all these ingredients together can be called a spectral triple and the operator a Dirac operator. So non-commutative geometry via spectral triples can be viewed as a kind of non-commutative Riemannian geometry. And that is because in the prototypical setting of a compact spin Riemannian manifold, Kahn showed that the geodesic distance can be recovered through purely operator algebraic data. So in that particular setting, there is really the choices of C-star algebra and Hilbert space and Dirac operator are uniquely determined. And so then outside of that setting, there's some choice in this, and that's part of the art in non-commutative geometry, is choosing these elements so as to be able to capture the geometry of a space or equip a space with a geometry.
So, sorry, what are the subscripts infinity on the D and the H in the last line there?
Oh, well, in this case, I'm thinking of the Sierpinski gasket, so this is just for on the entire space. So maybe I should have removed that maybe, yeah. So you can see that for a fractal that the usual definition of geodesic distance can be a problem because it requires the existence of sufficiently well-behaved paths. And so this is a motivation for developing spectral triples for studying fractality, is because therefore that obstruction is no longer an issue. Okay, so do there exist spectral triples for fractal curves, and do they capture the geometry of such curves in a sufficiently interesting way? Well, yes, there do exist such spectral triples. So one example would be Lapidus-Sarhad spectral triples, and they are built from spectral triples for circles. And so so these spectral triples are the following form. So for the unital C-star algebra, take the algebra of 2 pi r periodic functions on the real line, take the L2 functions with respect to normalized Lebesgue measure, take this canonical orthonormal basis and this differential operator, define it on that basis and take its closure. And then for the representation, take that of left multiplication operators. So that spectral triple is built from spectral triples of this form for circles. And so for a piecewise C1-fractal curve, for each parameterized curve, take one of these spectral triples for circles. And so you need to adjust each of the Dirac operators so as to maintain the compact resolvent condition. So that's the reason for the translation. And you have to adjust the representation. So you do the composition with the parameterized curves. And so what Lapidus and Sarhad showed is that this countable direct sum of spectral triples is in fact a spectral triple. So that's something that's not by necessity. But it is also importantly one that recovers the geodesic distance. And so for geometry in general, that's the essential idea, the essential importance of these spectral triples. And so in fact, these spectral triples are generalization. So in the case of the Sierpinski gasket, they are exactly spectral triples that were developed by Antonescu, Christensen, and Lapidus in that particular case. And in that particular setting, the same spectral triple captures not only the geodesic distance, but also the Hausdorff dimension and the Hausdorff measure. So again, a lot of multiple key aspects of the fractality of these spaces. So that said, is there a way to approximate such a spectral triple by spectral triples supported on simpler spaces? And well, that requires, so we use a generalization of Gromov-Hausdorff distance developed by our collaborator Latrémolière, who was in turn building on the work of Rieffel. And he recently extended this generalization of Hausdorff distance to the setting of spectral triples and appropriately termed it the spectral propinquity. And so our main result informally is that if we have a piecewise C1-fractal curve, so we've got parameterization and we have our notion of approximation sequence compatible with that parameterization, then the Lapidus-Sarhad spectral triple on each of those corresponding finite graphs converges in the sense of the spectral propinquity to the Lapidus-Sarhad spectral triple on the limiting piecewise C1-fractal curve. So that generalization of Gromov-Hausdorff distance is actually, so it was first defined on quantum analogs of compact metric spaces. And these quantum analogs of compact metric spaces are due to Rieffel. And they can be viewed as generalizations of Lipschitz algebras. So that's something to keep in mind as I go through the elements of the definition. So a quantum compact metric space is a pairing of the unital C-star algebra, and you have a semi-norm. And the semi-norm satisfies a form of Leibniz inequality. And also it vanishes precisely on scalar multiples of the identity. And then the associated Monch-Konorovich distance metrizes the weak star topology of the state space, by which I mean the set of positive linear functionals of norm.
L would be like the Lipschitz constant, you said?
Right,
I mean,
so this is an analogy to the Lipschitz semi-norm.
Okay.
So, yeah.
Okay.
So L is a semi-norm. And so in the particular,
Okay.
yeah.
Okay.
Right, so this is a semi-norm that in this more general setting, these properties are those that we want to carry into the non-commutative setting. And so when that semi-norm exhibits all those properties with respect to the C-star algebra, then that pairing qualifies as a quantum compact metric space. And so non-commutative geometry via quantum compact metric spaces can be viewed as a non-commutative metric geometry. And that's because here the prototype is a compact metric space. And all compact metric spaces are also quantum compact metric spaces. So, so here the unital C-star algebra being C of X, and the semi-norm being the Lipschitz semi-norm for the metric. But of course, you could still equip C of x with other choices of semi-norm, and that would define different quantum compact metric spaces so long as that suite of properties in the definition are satisfied. And to me, another important thing is that, so this map, the Gelfand transform, it's an isometry onto its image. So in that sense, the state space captures the metric information from the compact metric space. So to me, even in the commutative setting, then here's this enriched perspective of the original space. And so even further developing tools from non-commutative metric geometry would allow you to extract information from this enriched perspective. And so that's where, as a fractal geometer, I'm also very interested in further developing these techniques. And for me, this is also a very important, development in this is that, so in the case of the Cantor set, so Aguilar and Lopez, they were able to show that they were able to define different semi-norms that when you take their, when you equip the state space of C of x for x, the Cantor set with their corresponding Monte-Kontorovich metrics, you get, they agree on the space of characters, but they disagree on a dense subset outside of the space of characters. And so these are different, so they capture still the metric information for this space, but there's this additional sort of structure and perspective. So for this generalization of Gromov-Hausdorff distance to the setting of non-commutative geometry, we have a notion of quantum isometry. And what a full quantum isometry does, it's a star isomorphism between the C-star algebras that at the level of the state spaces, each equipped with their corresponding Monte-Kontorovich metrics, gives rise to an isometry at that level. And the Gromov-Hausdorff propinquity.
Actually different from asking that is LA and LB sort of commute with the pullback via phi.
Commute with the what?
With the pullback via phi of elements. Yeah, I'm asking whether, I'm trying to wonder why you really impose this condition at the level of Monte-Kontorovich distance and not directly at the level of these differential operator LA and del of B.
Well, I think here it would be because viewing the state space as equipped with this Monte-Kontorovich metric.
Yes.
And so that's at the level at which I would like the isometries. So,
okay, I mean, I'm fine. We'll just understand it.
Well, of course, there's also lots more for me to understand too, and to ask experts.
Yeah, basically, I guess what I was thinking also phi. Yeah, sorry. So I guess I was trying to understand whether, so you have phi that takes elements in A and returns elements in B, and you could ask whether phi of LOA of some guy is the same as L of B of phi of that guy. Right?
Well,
so
you can do it in either direction. It can be done in either direction.
Oh, so, okay.
Yeah.
Okay.
So actually, when you do the calculation, you do have to check it for both directions.
Okay.
So, and the Gromov, and again, in analogy with the classical setting, this non-commutative generalization of Gromov-Hausdorff distance, the Gromov-Hausdorff propinquity, is a complete metric on the space of all quantum compact metric spaces. And what does distance 0 mean for this non-commutative metric? Well, then it means that there exists a full quantum isometry between the two quantum compact metric spaces. And also, remember that all compact metric spaces can also be associated to quantum compact metric spaces. So it turns out that when I restrict to such quantum compact metric spaces, the topology induced by the Gromov-Hausdorff propinquity agrees with the topology of the Gromov-Hausdorff distance spaces.
That's where you said agrees with, but you have an
Well, it can be.
You have an inequality here that looks.
Okay, not agrees, it recovers, yeah. Right. So recovers, and that's actually a very, there's some things to be worked out about that still because of that inequality.
So this seems to say that X, the metric spaces, the embeddings of the metric spaces into the spaces of functions are, I'm actually confused, but continuous. This seems to say continuity of some embedding, no?
Right, so you can recover the topology. And so here I'm including a detail I don't normally too much include, but because we have a lot of Gromov-Hausdorff distance people here. I mean, so when you do Gromov-Hausdorff distance calculations and you can, you know, for two compact metric spaces for their disjoint union, define a metric on them. So when you do, when you calculate the Gromov-Hausdorff propinquity between two quantum compact metric spaces, there's a sort of general procedure by which you start. So you can always make you begin making a unidal C-star algebra. You can begin by taking their direct sum. And for your choice of semi-norm, you can put the two semi-norms you want, but then this part here, that's where every setting is going to be different. So this choice of this third component is going to be very different for each different setting. And in our particular setting, are the conditions that we put on the vertices were such as to be able to get what we needed in this case. And when you do the calculations, one of the things you can use is it turns out that that when you've chosen when you've made the right choice of third quantum compact metric space, then the Hausdorff distance for the state space of that quantum compact metric space with respect to the Monge-Konner-Ravitch metric for that semi-norm, that gives you a bound on the Gromov-Hausdorff propinquity between the two quantum compact metric spaces. So again, these are by analogy and not perfect. So, okay, so the spectral propinquity is not defined on all spectral triples. It's defined on a special class of spectral triples. It is those which induce quantum compact metric space structure. And so if you start off with a spectral triple, a natural quantum compact metric space to see if you can associate to it is to take first the unidal C-star algebra, and then for the semi-norm, take the norm of the commutator with the Dirac operator. And if that semi-norm, you know, with respect to the C-star algebra, unidal C-star algebra satisfies the properties required for a quantum compact metric space, then your spectral triple is a metric spectral triple. And so for this class of spectral triples, the spectral propinquity is a metric on that class. And it still remains to be seen what other additional properties this metric might have on such a class. So what does distance 0 for the spectral propinquity between two metric spectral triples give you? Well, it gives you unitary equivalence between the Dirac operators. It also tells you how well the representations play with each other. And also the underlying quantum compact metric spaces, it also gives you that level they're fully quantum isometric. And so when you given the role of the Dirac operator in non-commutative Riemannian geometry for extracting geometric information, then having this level of unitary equivalence between the Dirac operators is one of the motivations for applying this metric to the study and approximation of spectral triples. Okay, so here's a more formal statement of our results. So first, keeping in mind the particular setting of the Sierpinski gasket, we have a parameterization of it because it's an example of a piecewise C1-fractal curve. We have an approximation sequence compatible with that parameterization. We take each of the Lapidus Sarhad spectral triple constructions on the corresponding sequence of finite graphs, as well as that on the Sierpinski gasket. And each of those spectral triples happens to be a metric spectral triple, so they each induce quantum compact metric space structure. And then with respect to the spectral propinquity, each of these spectral triples more gets closer and closer, or approximates that on the limiting fractal, the Sierpinski gasket. And our argument, so we came up with our framework, and our arguments are such that if you replace the Sierpinski gasket with any piecewise C1-fractal curve and any approximation sequence that has the properties that we gave in our definition, the same arguments still hold. So our arguments hold for any piecewise C1-fractal curve for which you can identify an approximation sequence. Okay, so so I've worked on the setting of the stretched Sierpinski gasket. So the stretched Sierpinski gasket is another important example of an analysis on fractals, but it's one on which there is a lot of active results going on. So you can see already that instead of being self-similar, it's self-affine. But in a way, it's natural to try to see what results from the Sierpinski gasket can be generalized to a setting of the stretched Sierpinski gasket, because it's in a way a sort of relaxation, because one way to get it is to replace each of the vertices in the Sierpinski gasket with intervals of a certain length, and that's what this alpha parameter controls.
Sorry, why do you say it's self-affine but not self-similar? It sort of looks self-similar.
Well, I didn't mean self-affine. Okay, the iterated function system, some of the are not contraction mappings. So you can't, so actually, okay, when you define this then, so it's not self-affine, so it is self-similar, but one of the ways to define this via a iterated function system is there are 6 contraction mappings. And so again, starting off with a triangle, and you map for the first 3, that triangle to each of these, and then to an interval for each one. So you collapse it to.
Those edges are there.
I see.
If you take out the edges,
Then it would be self-similar. Okay.
Yeah.
I see. The edge is the hexagon.
Yeah, well, so the edge, so a lot of the problems come from the edges. So also, besides making it sort of fundamentally different media that would model this, it's also, this is not a piecewise C1-fractal curve because the vertices are not dense. And
all right.
Yeah. And so it does have fractional Hausdorff dimension. Unfortunately, it depends on that parameter alpha.
Sorry, what is the alpha here?
So the alpha
determines how small the triangles are in the corners?
Well, how small these intervals are. So as
Okay,
alpha goes
thanks.
to 0, then.
I see, then the interval is shorter and shorter.
Right. So that's something that's in a paper too, is actually even the Hausdorff distance, the Hausdorff distance convergence. So that's Patricia Alonso Ruiz and Uta Freiberg showed that. And so one of the things I've worked out is that also as that parameter goes to 0, so Andrea Rauser Rivera, so she showed that the Lapidus Sarhad spectral triple on the stretched Sierpinski gasket, so that construction can be adapted to the stretched Sierpinski gasket to get a spectral triple. So I showed that that spectral triple, that as the parameter goes to 0, then it approaches for the spectral propinquity. The Lapidus had spectral triple on Sierpinski gasket. And well, what I'd like to do is figure out, use this as a prototype for definition of a class of almost piecewise C1-fractal curves. So here's the Sierpinski tetrahedron. So, okay, what would be an appropriate generalization or construction? What would be an appropriate spectral triple for Sierpinski tetrahedron, along with a notion of approximation, and what would be a spectral triple that captures essential aspects of this geometry, and along with the appropriate notion of approximation. And for me, this is kind of one of my holy grails, is the Sierpinski carpet. And well, Sierpinski carpets are fundamentally different from Sierpinski gaskets. There is the same tools that can be applied to Sierpinski gasket type fractals can't be applied to Sierpinski carpet type fractals. And one of the main ways to see the difficulties, so Sierpinski gaskets, you can totally disconnect the fractal by removing a finite set of points, but that is impossible for Sierpinski carpet type fractals. So they're examples of infinitely ramified fractals. And so in a sense, a lot of tools that I've tried to acquire this year have been things that I hoped would help me in eventually developing spectral triples on Sierpinski carpets. And that's everything from early in this year wanting to learn about quasi-symmetries, because there are a lot of quasi. So here's another sort of homeomorph. These are round Sierpinski carpets at the bottom. And those are homeomorphic to Sierpinski carpets. So there are many different quasi-symmetry classes of those. And also there's a spectral triple involving limit sets of Kleinian groups. And so these are all sort of like tools that I've been working on trying to acquire for eventually Sierpinski carpet type fractals. And so see other directions or future work. So, well, again, there is this idea of how to come up with the right notion of generalization of manifolds that would include fractals. There's classification of C-star algebras on fractals. So my original motivation for this was, well, with respect to the Gelfand-Naimark theorem, if you have C of X for X a Cantor set, then that's star isomorphic to unidal commutative approximately finite algebras, but outside of that setting, so even for Sierpinski gaskets, it's not known what kinds of C-star algebras those are. And so, of course, from getting to be here and getting to be in George's group, I hope to, now I think I might try to see how I could use elements from classification for identifying and studying such C-star algebras. And of course, this would also help since these are key ingredients in quantum compact metric spaces and in spectral triples, then that would also be a basis for the further development of fractal manifold via means from non-commutative geometry. And then lastly, well, are defining instances of fractality that are in a sense truly non-commutative. Are there fractals that can only occur in a non-commutative setting? So for instance, the Gromov-Hausdorff propinquity is a complete metric. Well, we have a complete metric. Maybe you could take the right sort of set of contraction mappings and define could you define an interesting enough like fractal space with respect to that complete quantum metric. So that's just an example, but because there's so many non-equivalent definitions of fractality, then there are a lot of possibilities for their definition and study and understanding. Thank you.
Thank you for other people talk. Are there questions? Let's see. Are there questions from the online audience? Nicola has a question from in the room.
Yeah, thank you very much for this nice overview. I was wondering, is there a way, or